In this presentation, we discuss our position paper about learning grammar in confined worlds, which was accepted at IWSDS 2020. In this position paper, we argue that modern machine learning approaches fail to adequately address how grammar and common sense should be learned. We advocate for experiments with the use of abstract, confined world environments where agents interact with the emphasis on learning world models. Agents are induced to learn the grammar needed to navigate the environment, hence their grammar will be grounded in this abstracted world. We believe that this grounded grammar will therefore facilitate a more realistic, interpretable, and human-like form of common sense. As humans, we navigate very complex environments every day, full of agents, interactions, transactions, and different types of communication. It is generally well understood that humans create abstract models of the world from which they draw inferences. In the example of this maze, one would thus make a decision about which direction one would take based on that abstract model of the world. It makes sense that such world models are a byproduct of the necessity to deal with everyday tasks. The complex details of all possible interactions are abstracted to a level of detail that best suits the ability to navigate the world. Most machine learning applications lack such interactions and reduce training to one or two objectives. For example, to achieve the best caption, to achieve the most fluidity, and so on. Some models excel at complex natural language benchmarks such as glue. In this figure, we see how consecutive models have improved on glue tasks to the extent that they achieve superhuman performance. On tasks that appear simple to humans, these models still fail most of the time. The types of mistakes they make point to a limited understanding of how the world works or how objects interact with the world. This slide shows some examples of how a recent language model GPT-3 fails at such tasks. Notably, the model doesn't understand that a foot cannot have any eyes. A better goal would be to achieve a type of world understanding or common sense which we describe as the ability to understand things as they really are. As an example, the neural network on the previous slide did not understand the true nature of a foot, otherwise it would have known that a foot cannot have any eyes. To achieve this type of common sense, data should be processed and understood with respect to a broader physical context. To answer the question about how many eyes a foot has, it should be understood what a foot is, what function, shape, and characteristics it has, and how it interacts with the world. While common knowledge is often implicit in communication and most likely results from world interaction, humans do use language to transmit complex information that relates to the world. It is therefore sensible to study how grammar and common sense relate to each other. We posit that making oneself understood is a task that humans learn as part of the objectives in everyday life, and thus human grammar is grounded in world interaction too. In our view, structured language facilitates the navigation of world models and common sense. Grammar then provides a set of tools that can be used to relate concepts and objects in our internal world models. These models could therefore facilitate a more elaborate common sense understanding. To extrapolate this idea to machine learning, one could deploy models that are capable of learning grammar in an environment that induces them to learn it. Current approaches to natural language processing tend to rely on more and more complex data sets that are solved with larger and larger models. Meaning representations are mostly constructed following the distributional hypothesis, grounding symbols in other symbols instead of in reality. As a consequence, models learn to exploit word co-occurrences and unintended features in the data set. This leads to non-transparent calculations and outputs that conflict with human understanding of the world. An interesting avenue is to place models in virtual or physical environments that are affected by a temporal component. This idea has been expressed by other researchers, yet the push towards higher complexity has perhaps complicated this line of investigation. Many controlled experiments are possible which could advance our understanding of language learning. By setting up a confined world, different priors and models can be investigated. Rather than setting up 3D physical or photorealistic simulation environments with complex interactions, we suggest abstracting the physical world to a set of parameters of increasing complexity. Some work in this direction has been done, yet many more abstractions, tasks, situations, agents, and interactions remain to be explored. While some have advocated for a semantic representation formalism based on second order intentional logic, we believe that such agents should form their own implicit models of interactions and meaning. Our suggestion is therefore to focus on architectures that mirror the innate capability of brains to learn syntactical and morphological complexities of language rather than relying on pre specified symbolic formalisms. Artificial agents could, for example, exploit model architectures that explicitly detect disagreement between language morphology and the state of the world. As a concrete example, for the sentence, "The apples are falling," a model might be designed to detect that the sentence contains a plurality of apples as expressed by the subject and verb and align it with observations of multiple falling apples from the evolution of the world state. We thus propose to investigate different model structures and learning algorithms in confined environments. Concretely, we propose abstracted environments that contain spatial and temporal axes, perception, grammar, interaction, and objectives. Objectives should prompt agents to implicitly learn a basic model of the world and the language rules to navigate it successfully. In these confined worlds, the importance of teachers, including whether their language supervision is needed at all, as well as the elements needed to express language in relation to the world, can be investigated. We believe such experimentation will lead to a better understanding and new research directions and enable valuable applications. Thank you for your attention.